Alright, so now we're on to part B of this exercise. Essentially what I'm going to do is I'm just going to keep going until my computer starts to crash. So I don't know if that'll be at the end of part B or if I'll start to get through some of the other parts as well. Here we start to get into one of my other issues with this exercise. My main issue with this exercise is that I feel like there's a lot of tools that we don't really have at our disposal yet that I would really like to have to do this problem, and it would sort of get rid of a lot of all the really small minor details that you have to take care of and let you get to the real meat of the problem. So maybe they could have held off on this exercise until later, or well then again, since I guess you would need some more point set topology, mainly, maybe some analysis. Yeah, I don't know. Whatever, let's just keep going. The other issue that's going to come up here is that this exercise is horrible with naming functions. So we want to show that there is a C infinity function g here, blah blah blah. Hint, if f is a C infinity function which is positive on 0 to epsilon and 0 elsewhere. Okay, so first thing we want to do is we want to get this function f that they talk about in the hint. And we're going to use that f to find g. Now, the way that we're going to construct this function f is using the function f from the previous part. But of course we can't call that f's, so let's let f tilde be the function from part A. Here, let's write it like this. Now what I want to do is, if you remember from part A, we had f tilde was like this function. It was like a bump here. I mentioned this at the end, so this is -1 and this is 1. And this is f tilde. What we want is a function that is a C infinity function which is positive on 0 to epsilon. So what we want is something that, let's see, if this is epsilon, we want it to look like this. This will be our f. And so what we want to do is we sort of want to make this function so when we plug in 0 here into f, we're actually plugging in -1 to f tilde. And when we plug in epsilon into f, we're plugging in 1 into f tilde. So what we want to do is we want to send the interval 0, we want to send 0 to -1 and epsilon to 1. And we can go ahead and do this with a linear function. So if we have a linear function, so let's see here, so y equals mx plus b will be our linear function. Now if we send 0 to -1, that means that the y-intercept is -1, so b is going to be -1. Now if we send epsilon to 1, so here y equals mx plus b, that will become 1 equals m epsilon plus b, which is -1. And so we have 2 equals m epsilon, or m equals 2 over epsilon. Okay. So what we're going to do is we're going to let f of x equal f tilde of 2 over epsilon times x minus 1. Let's see here. F is C infinity because f is a composition of C infinity functions. And like I discussed in part A, compositions of C infinity functions are C infinity. You can prove that yourself using the chain rule if you want to. But again, f tilde is C infinity because we proved that in part A. And this thing on the inside here, this is f tilde applied to a linear function of x. So this linear function of x is linear, and therefore it's c infinity. So that's why f is c infinity. Okay. So let's see here. We have f as a c infinity function. Let's see here. Since f tilde is supported, and I'm going to come back to this word, on the interval 0 to epsilon, and no, f tilde is supported on -1 to 1, and and y equals 2 over epsilon x minus 1 sends the interval 0 to epsilon to the interval -1 to 1. F is supported on 0 to epsilon. And when I say that f is supported on 0 to epsilon, what that means is that if you take any x in the open interval from 0 to epsilon and evaluate f at that x, then you'll get a positive value. But if you evaluate f at some point outside of that open interval, then you'll get 0. That's what it means to be supported on an open set in this case. Okay. So f is indeed a c infinity function, which is positive on 0 to epsilon and 0 elsewhere. Because this being positive on 0 to epsilon and 0 elsewhere is equivalent to saying that f is supported on the open interval from 0 to epsilon, just by the definition that I just gave. Okay. Let's continue. And now we're going to do what the hint says. Let g of x be defined to be equal to the integral from 0 to x of f divided by the integral from 0 to epsilon of f. Let's see here. Okay, so the integral from 0 to epsilon of f is, it's just a constant. Because even though f is a function, we're integrating f from 0 to epsilon, so that's just going to give us some number. So this is a constant. What else do we have? The function integral from 0 to x of f, this is continuous, because if you have a continuous function, then the function if you have a continuous function f, then the function defined by taking the integral from 0 to x of f is also continuous. And, well, I guess, I forget if that's been discussed in the chapter. Talking about integrals just at this point in your mathematical career is a little tricky itself, because you can't really talk about integration the way you really want to be able to until you learn measure theory. And unfortunately, you can't just ask someone to, like, take a course in measure theory, and, well, I don't know if, well, usually measure theory is, like, at the grad level, it's enough for, like, 2 to 3 months of a real analysis course. So to say, like, that it comprises an entire course of measure theory, of course there's enough measure theory out there that you could make an entire course about it, but typically it's mixed in with other things. Anyways, to get enough measure theory to define the Lebesgue integral, until you do that, it's hard to talk about integrals rigorously. I mean, Riemann integrals work fine, but yeah, even that, we haven't talked about Riemann integrals in this textbook, I don't think, yet. But just trust me at this point that the integral from 0 to x of f is a continuous function. If you don't believe me, which you shouldn't, then either try to prove it yourself or look up a proof of it. Okay, so this is a constant. So this function is continuous. And if we want to take the nth derivative of g, well, okay, so the fact that the integral from 0 to x of f is continuous implies that g itself is continuous. So we have enough information to tell that g is continuous. Now, as for the derivatives of g, the nth derivative of g, if we take a derivative greater than or equal to 1, what is this going to be? Well, we're going to keep the 1 over integral from 0 to epsilon of f, because again, that's just a constant, so that stays there. And then what we're going to do from there is we're going to take n derivatives of the integral from 0 to x of f. But by the fundamental theorem of calculus, that's just the same as taking n minus 1 derivatives of f, where of course the 0th derivative of f is just f itself. Which is continuous since f is c infinity. Right? The fact that f is c infinity implies that the n minus first derivative of f is continuous, and therefore the nth derivative of g is continuous. So thus g is c infinity. Alright. So now what else do we want to do? We want g to be... So what do we want g to look like? We want g to be... if we go from 0 to epsilon, then once we get to epsilon, we want to be at 1. If we're to the right of 0, we want to be at 0, and we sort of want to increase from here to here. So g is going to look something like this. If you're to the left of 0, it's just 0. If you go from 0 to epsilon, the function will increase to 1, and then if you go to the right of epsilon, you'll be at 1. So we're trying to prove that g looks like this, so let's prove this. If x is less than or equal to 0, then since f is 0 on the interval from x to 0, we have integral from 0 to x of f. Well, if you have x less than or equal to 0, then this is just, you're just integrating, let's see here, if you put the leftmost point on the bottom, then it's the integral from x to 0 of f, and you have to put that minus in there, because of how integrals work. But because f is 0 in this region, you're just integrating the number 0, or integrating the 0 function, and so you just end up with 0. And so g of x is going to be integral from 0 to x of f over integral from 0 to epsilon of f, which is just 0 over whatever that number is, and so it's just going to be 0. Alright? If x is greater than or equal to epsilon, then since f is identically 0 on the interval from epsilon to infinity, again, this means that if you plug in if you take any x in this half-open interval from epsilon to infinity and plug it into f, you'll get 0. So anyways, what this tells us is that g of x is going to be, let's see here, integral from 0 to x of f over integral from 0 to epsilon of f. Now, here, the integral from 0 to x, because epsilon is going to be between 0 and x in this case, we can break this up into the integral from 0 to epsilon of f plus the integral from epsilon to x of f. And we divide by integral from 0 to epsilon of f. Now, since f is 0 on this interval from epsilon to infinity, the integral from epsilon to x of f is going to be 0. And so what we're going to be left with is the integral from 0 to epsilon of f over the integral from 0 to epsilon of f, which is just 1. Okay, so that's good. Finally, well, we actually don't necessarily need we don't need this function f to be increasing. What we want to prove is that the range of g is the interval from 0 to 1. But we're going to prove that by proving that g is increasing from 0 to epsilon. So finally, g prime of x, well, this is equal to, well, when you take the derivative of the integral from 0 to x of f, you just get f of x. And again, we're dividing by the integral from 0 to epsilon of f. Now, by construction, f is positive on the open interval from 0 to epsilon. And the denominator is just a number. So this is... Okay, so this is... Well, even if you're not on 0 to epsilon, this is always going to be greater than or equal to 0. So g is increasing. And thus, g maps r into 0 to 1. Now, why does that follow? That follows because we know that g takes on 0 to the left of 0, to the left of x equals 0, and g of x takes on 0 to the left of x equals 0, and g of x takes on 1 to the right of x equals epsilon. So the only place where g could possibly not be in the closed interval from 0 to 1 would be in between 0 and epsilon. But since it's increasing, for any point between 0 and epsilon, f of that point must be between 0 and 1. And that's by continuity. And is that the mean value theorem? Yeah, it's one of those super important calculus things, which I guess maybe we haven't proven at this point. There's a bunch of things in here that I'm not quite sure if we've rigorously proven at this point. Just sort of why I really like how Baby Rudin really just starts from scratch and builds up everything. So anyways, g is increasing, and thus g goes from r to closed interval from 0 to 1, and that's what we wanted. We wanted a c infinity function, which goes from 0 to 1 from 0 to epsilon. We wanted a c infinity function that looks like this function g that I drew here, and we got one, and so we're done with this part.